Welcome everybody. We will begin the formal presentation now. And just a quick note that I know they'll touch upon a little bit more, but Robert, our speaker, is in the mix of that bizarre weather where he may lose power once again. He did earlier. So bear with us if that does happen. So passing this off to you, Anne, and thank you.
So welcome to New Bedford Science Cafe, everyone. Here's everyone's health, happiness, future. And Robert, welcome. Robert Johnson, welcome so much to you. Robert's in Albuquerque, where there's been a huge drop in temperature, and he'll tell us more about this. I first want to say Miles Grant is here fielding questions. Miles, why don't you introduce yourself?
Hi, I'm Miles Grant. I'm Director of Publications and Media Relations at Woodwell Climate Research Center. We're recently been renamed from Woods Hole Research Center to honor our founder, George Woodwell, and also make clear that we work primarily on climate change. We're located in Falmouth, Massachusetts, and I live in Marion.
Super. So Miles is going to join us a little bit later. Robert's going to talk for about 20 minutes. But again, I want to also first thank the New Bedford Whaling Museum for partnering with New Bedford Science Cafe, providing us with Zoom. Jocelyn Nunes, who you just saw, is, I call her the museum's Zoom queen. She has just been fantastic in helping us with this technology. The recording, by the way, of each of our science cafes becomes available within a week, and you can find it on the YouTube channel for the museum or on our website, New Bedford Science Cafe website. So it really is a tremendous honor to have Robert Johnson with us, physicist who's discussing laser beacon adaptive optics and the major advances it allows astronomers. I want to mention that it's also thanks to his aunt, Rachel Kolb. I just made you much younger, Rachel. She's a steadfast science cafe goer, and she put us in touch with Robert, her nephew. And basically, Robert was all set to come to New Bedford, greasy luck, but COVID struck, and obviously he can't be here. He's in Albuquerque. Robert Johnson is a senior scientist at Kirtland Air Force Research Laboratory in Albuquerque, and because of his and his team's major accomplishments in the field of adaptive optics, he recently was awarded the Air Force's most prestigious science award, the Harold Brown Award. He received a Master of Science in Applied Physics from the Air Force Institute of Technology at Dayton, and his Ph.D. in Optical Sciences from the University of Arizona, Tucson. So he's here to tell us more about this amazing technology that is being built into every large telescope around the world, which has the ability to take very high resolution photos of objects in outer space. So on to you. Where did Robert go to? Oh no. This is, everybody, this is what happened when we were warming up. Robert's power went out. We're just gonna have to chat for a little bit and hope he reappears. That's what happened a few minutes ago. He told, Miles, do you want to explain?
Well, so Robert Johnson lives in Arizona, I believe, and they've been having some wild weather out there. I think a lot of places had seen temperatures around 90 yesterday, had dropped into the 30s today, had seen some strong snowstorms. Robert had warned that the temperature was going to drop well below freezing tonight. He had lost power momentarily while we were in the prep session, and apparently he's lost power again. During the prep session, his power came back on pretty quickly. It was just a flicker. Once his modem fired back up, he was able to rejoin us, but we'll have to wait and see if he's going to be able to join us now. Obviously, we're very thankful for all of you to have joined us on this Tuesday evening, and we're hopeful that he can rejoin us, but we're trying to buy a little time until he can. Obviously, the weather out west has been a huge red flashing light of climate change and our energy choices going forward that California has seen, especially Southern California in the Los Angeles area, has seen its all-time high temperatures, some of its all-time worst fires, definitely some big warning signs of climate change going on out there right now. Obviously, power disruption, another impact of climate-fueled extreme weather, one we're dealing with right now. This is a flashback to my TV news days when you would have a extreme weather situation and the anchor would just have to go on and talk about what was going on until we figured out what the next thing would be. And that's kind of what we're doing right now. Again, Robert rejoined within a few minutes during our prep session. We're just hopeful that he's going to be able to hop back on shortly here.
So can everybody hear me? I realize I'm a little faint. Is that better? I cannot find the volume turn up here, so I just hope everybody can hear. I thought in the meanwhile, we won't wait that long, but I can tell you what's coming up in the future at least, and tell you a little bit more about our Science Cafe. We meet monthly. I guess most of you have probably been coming. In October, Tuesday, October 6th, we have Jamie Jacquart, Jamie is the assistant head of the Sustainability Center. He's going to be talking about net neutrality and how to get there from where we are by the year 2030. I'm still a little faint, I guess. Then November's visitor is going to be Jonathan Curtis. Yay, you're back.
And I think we should get right to Robert here and get his presentation going so we can get as much of it as we can in.
All right, sorry about that. Yeah, there's no such thing as climate change. I just want to say that. We had record heat yesterday and now we're at a winter storm warning today. Again, so I'm Robert Johnson. I work at a place called Starfire Optical Range. Our power is still just coming up here. Sorry. And trying to get the slide on. All right. And I'd like to thank Ann Parsons for arranging this for me, and to my aunt and uncle, Rachel and Thomas, for introducing me to Ann. So I work for the Air Force Research Lab, and we run telescopes here in Albuquerque, New Mexico, and in Maui. We do this thing called space domain awareness. That's just a government speak way of saying that we do research to try to figure out what satellites are up in space around the Earth and maybe even around the moon, and are they friendly to our satellites, and can they harm our satellites, that sort of thing. We're part of AFRL. We have different research groups all around the country. We also have research folks in Tokyo, London, and Washington, DC, and Santiago, Chile to fund university research. So if you're a university researcher, please, if you have interesting basic research you think the Air Force would be interested in, contact our offices there. All right, so why do we care about monitoring space? Well, as you probably know, we rely on satellites for a lot of different things. Communication, navigation. I'm sure most of you have a cell phone with a GPS receiver in your cell phone that tells you where you are almost anywhere on the planet. And we also have satellites that help us monitor the environment and climate change and weather. So all of those things are very important to our country, not just our military. And so we find it really important that we be able to know what's going on in space, and are people doing things that may affect our ability to freely operate in space. All right, so the subject of my talk is laser beacon adaptive optics. If you've ever gone outside on a clear night, you can see the stars twinkling, and that's nice for just to observe, and it's nice for nursery rhymes, but it causes a problem for astronomers. Isaac Newton first noticed this effect over 300 years ago when he looked through his telescope. You notice on some nights he could get a clear view of the stars and the planets, but on some nights it was much worse. And so what is happening is that, light as it leaves a distant star or a galaxy travels thousands of years or even millions of years. and it gets to the Earth's atmosphere. And because the atmosphere is not uniform, there's hot air and cold air in the atmosphere, and that's driven by the sun heating the Earth mostly. And so when this light hits the atmosphere, if part of the atmosphere is colder than other parts, then that light travels more slowly, and it gets to the astronomer's telescope at a different time. And the effect of that is basically you end up with a blurry image. So even if you have a very large telescope in a nice place, let's say at the top of a mountain, if your telescope is really big, and astronomers like big telescopes for two reasons. One is they can collect a lot of light, so you can look at dim things. The other reason we like big telescopes is as the telescope gets bigger, your resolution gets better. So as the diameter of the big mirror or the big lens of the telescope gets bigger, you can make sharper and sharper pictures, which is important for astronomy. And so the effect is that even if you, because of the atmospheric turbulence, the resolution of a large telescope in a pristine location on the top of a mountain has about the same resolution as a backyard telescope, say a 4-inch backyard telescope. So that's been a problem. So it's been a problem for, like I said, 300 years. So what can you do about this? As I alluded to before, you can put your telescope at the top of a mountain, and you'd like that mountain to be in the middle of an ocean or near a desert. So some of the best places in the world to do astronomy are the Hawaiian Islands, the Canary Islands off the coast of Africa, and Chile. Those are some of the best places because the air is very still around, the sun doesn't have a chance to heat the ocean very much. So the air is very still. So that's one thing you can do, but that only gets you so far, right? So something else you might do is launch a telescope into space. So I'm sure all of you are familiar with the Hubble Space Telescope, which was launched in 1990. But as you know, there was a problem with that telescope when it was launched. They made a mistake on the ground when they were polishing the mirror, and the pictures weren't that good to start out with. And we had to send a shuttle up there to fix it. So it's very expensive to launch telescopes into space. And their size is limited to basically the size you can fit in a rocket, and which back then was about 2.5 or 2.4 meters. So astronomers have been thinking about this problem. And in 1953, an astronomer, a US astronomer named Horace Babcock, proposed an idea to deal with this problem, this atmospheric turbulence problem. And his idea had all the pieces that were required to solve this problem. He had a way of measuring the distortions caused by the atmosphere, the turbulence, and he had a way of correcting it. But the technology really didn't exist and wouldn't exist for another 25 years for him to do that work, or for anybody to do that work. Let's see, in 1980, what was the Phillips Research Lab later became the part of the AFRL, Air Force Research Lab. We got a $100,000 grant from ARPA, which is the predecessor to DARPA. I'm sure you know about that, the Advanced Research Projects Agency, the people who invented the internet. They gave us some money to work on this problem, and we started working on it. We were teaming up with researchers there at MIT Lincoln Laboratory in Lexington, Mass. And in 1981, there was a meeting in Boston to discuss this, this problem. And DARPA was pretty excited about the meeting, and they decided to classify everything. So all the work that the military was working on went underground at that point. And so in 1982, we got the first images of satellites from our telescope, one of our 1.6 meter telescopes in Maui. But the problem with that is all the light from the satellite was used to measure the wavefront, and that left very little light to actually make an image. So we needed a way to create an artificial light so that we can use the artificial light to measure the turbulence, and then we'd have light left over to make images, to take pictures of the satellites. So we briefed the problem to this group called the Jasons. I don't know if you're familiar with them. They're kind of a think tank that's drawn from industry and academia to advise the military. And basically, the best you can hope for when you brief the Jasons is for them to not shut down your program. They love closing down programs. So our tiny little program funded by $100,000 here in Albuquerque was in jeopardy. And when my mentor, Robert Fugate, briefed the Jasons, one of the members there said, hey, if you need an artificial light, why don't you use the sodium layer? And the folks at the time working on this didn't even know anything about the sodium layer. The sodium layer is a layer of atomic sodium that's high in the atmosphere. It's about 90 kilometers up. It's deposited by micrometeorites that bombard the atmosphere all the time. And these things normally burn up as they enter the atmosphere. They're left over from asteroids, basically. And they bombard the atmosphere and they burn up and they leave some sodium up in high in the atmosphere. And if you know anything about sodium, if you've ever seen a sodium vapor lamp as a street lamp, it's a bright yellow lamp. That's essentially the same thing that's up there in the mesosphere, 90 kilometers up. He said, well, why don't you try using that? And the guy that proposed this is Will Happer. And Miles, you might know about him. He's a climate denier. So he led to this idea that has revolutionized astronomy. But anyway, a little side note, sorry about that. All right, so we started working on another technology called Rayleigh beacons, and that's using lasers that are scattered off of air molecules low in the atmosphere. And, you know, as some of you probably know, Rayleigh scattering is what causes the sky, what makes the sky blue. So that works really well, but it only works low in the atmosphere. So you're only measuring the turbulence caused by the lower layer of the atmosphere, maybe the bottom 20 kilometers. MIT Lincoln in Lexington, they took the harder problem. They said, we're gonna work on sodium beacons. While we here in Albuquerque, we're working on Rayleigh beacons. And DARPA loves to work this way. They like to pit one group against the other and, you know, have some friendly competition. And we had our first results in 1983, and MIT Lincoln had the first results in 1988. And that was just to prove that you could use a beacon to measure, a laser beacon to measure turbulence. We got our first AO corrected images, adaptive optics, short for AO, in 1989. And things were going along great. We were making a lot of progress, working together and competing. But in 1990, it looked like some French astronomers would probably end up scooping us within 3 years. And we, you know, we couldn't allow that. So we convinced DARPA to let us declassify our research and present it to the world. And luckily, they allowed us to do that. So in 1990, they approved us to declassify this technology. And so in May of 1991, we presented the results to the American Astronomical Society. And it was a big hit because astronomers, like I said, they had known about this idea since the 50s and been working on it, but they didn't have the budgets that we did during the Cold War. So we were able to make a lot of progress. And so the National Science Foundation funded a bunch of researchers to come here to Albuquerque and to learn what we did, how we developed this technology, and what the kind of you know, the tricks are to get it to work, right? It's a big engineering problem. So after that, practically every large telescope in the world started retrofitting their telescopes to use adaptive optics, laser beacon adaptive optics. One good example of this is the Keck telescopes. There's two 10-meter telescopes on Mauna Kea in Hawaii, on the Big Island of Hawaii, and they retrofitted one of those for laser beacon adaptive optics. And then there came a bunch of proof of concept telescopes. There were two really big ones in Arizona that I worked on as part of my PhD dissertation. And then there was 4 other telescopes called the VLT, down in Chile that the European Southern Observatory worked on. And those were all proof of concepts to get us to where we really need to be. We want to make some really large telescopes. So this decade, we've got 3 big telescopes that are supposed to be coming online. There's the European Extremely Large Telescope, or ELT. That's a 39-meter telescope. And remember how I said the diameter of the telescope determines your resolution. And that's only true if you have laser beacon adaptive optics. So these telescopes were designed from the ground up to use adaptive optics rather than as a retrofit. So the European ELT is going to be placed in Chile. That's 39 meters. And then there's 2 US-led telescopes. The 30-meter telescope, which we don't know where it's going to go. You probably heard in the news of some controversy about putting another telescope at the top of Mauna Kea on the Big Island. There's a lot of angst over that. So the backup location for that telescope will be La Palma in the Canary Islands off the coast of Africa. It's part of Spain. There's lots of big telescopes there as well. And then a third telescope is the Giant Magellan Telescope. That one is 7 8.4 meter mirrors put together to make one giant 27-meter mirror, and that's going to be in Chile. So the 2 US-led efforts are, they're led by universities and consortiums with other countries as well participating. Our science budgets for astronomy in most countries are very small compared to the rest of our budgets. So we have to pool our resources together to do astronomy. These telescopes are big and expensive. The European ELT is about $1.3 billion, but I think it's going to go over budget. And the 30-meter telescope and the GMT, Giant Magellan Telescope, are about $2 billion each. So they're not inexpensive, but definitely cheaper than a space telescope today. So what kind of astronomy can you do with these telescopes? Well, you can, well, my light went out. The power is flickering here. All right. All right. So what can you do with these telescopes? You can look, you can study the early universe. So as you look out at light from distant locations, it takes time for that light to get to you. So if you can look at very dim things, you can look at, you're actually looking back in time. So you can see the formation of galaxies in the early universe. So you can kind of do time travel. We can study black holes. We've discovered a supermassive black hole using adaptive optics at the center of our galaxy, the Milky Way. And we see stars orbiting that black hole. And we think these supermassive black holes exist at the center of all galaxies, all spiral type galaxies. We can study dark matter and dark energy. This is a really interesting topic. But if you can't actually see dark matter or dark energy, but you can see its effects through gravitational lensing and how it affects this rotational speed of galaxies. What happens is we see that galaxies spin faster than we think they should, given the mass of the material that we can see, the mass of the matter that we can see. So one explanation for that is there's some sort of dark energy, dark matter, causing them to rotate faster. It's like someone skating in an ice rink, and if, as you pull your arms in or you hold some barbells in your arms, you'll spin faster. It's that kind of thing. You can look at star and galaxy formation, and probably one of the most important things that I think we can do with this sort of astronomy is look at extrasolar planets. We've come up with a bunch of ways of detecting planets around other stars in our galaxy. A lot of those look at variations in the intensity of the star as, well, that's weird, as a planet passes in front of it. But you have to make observations for a very long time, and you can't see really small things because it would cause the intensity, the light coming from that star, to vary just a little bit. We also look at how planets push and pull on the stars and cause their light to shift in frequency. And we can measure those small shifts in frequency to detect the presence of planets, but neither of these is actually looking at the planets. And they're sensitive to looking at very large planets like Jupiter, but not so much for what we call habitable planets that are in the habitable zone. And for us, that's the place where water can exist on a rocky surface. That's what we think, or maybe even a gaseous surface, but probably a rocky surface. So we think these telescopes will be able to look at those extrasolar planets, planets around other stars, and maybe measure the presence of water by looking at light reflected from the star off the planet, and also maybe the presence of chlorophyll in plants or other signs of life. So to me, that's quite exciting. And these telescopes are all supposed to be coming online in the next decade. All right, but so that's the entirety of my talk. I went a little bit over, I apologize for that. So I think Miles and Anne, we're ready for questions. And hopefully the power will stay on. It keeps flickering though.
Robert, first of all, thank you for that talk. We really appreciate it, especially in what it sounds like the beginning of a trying night. We hope things settle down there. First, I wanted to start you with one about one of the more fascinating aspects of this research. One of our viewers asks, is it true that if you were looking from Albuquerque at a car in LA, you would be able to tell the difference between the headlights?
Yeah, that's true. That's true. And that's, but if you look from Albuquerque to LA, the Earth would get in the way unless you're a flat earther. So, but if the Earth were flat, you'd be able to look at the headlights. Another way to look at it is we try to detect very dim things next to bright things. That's the extrasolar planet problem, because there's a big star there and we want to see that planet next to it. And that star has so much glare, like if you looked at a car headlight, you get a lot of glare and you can't see who's in the car. But with the development of these technologies, you could look at that car in LA, and that car could have its bright lights on, and there could be a candle on the hood of the car or a firefly flying around the hood of the car. And that's the goal, to be able to detect that firefly or that candle. And that's where we are now.
Another question from one of our viewers. What are some of the big questions that you think will be cracked open by these new telescopes, and what are you most excited about?
Well, like I said, I think it's the extrasolar planet. Are we alone in the universe? Are we the only planet with life on it, or are there other planets with life on it? So to me, that's the biggest secret that we can unlock.
Another question for you. Do these telescopes have any extra usefulness in our own solar system? Is there anything that we can glean from it?
Oh yeah. We use these telescopes to study, like our telescope, we use it to study asteroids and moons orbiting around asteroids. This helps in planning missions to the asteroids. As you know, NASA has launched a couple of missions to asteroids, as well as the European Space Agency. And by studying these asteroids, we think they're left over from the formation of the solar system. So by studying them, we can learn something, also comets, right? We can learn something about how the solar system was formed. And just by observation, we can determine the density of these asteroids and tell what type there are. There's basically two types, and we can tell which type. And so there's also a lot of planetary astronomy, studying the moons around Jupiter. There's some really interesting moons going on there. There's Io is the most volcanically active body in the solar system. There's a planet with more water than Earth. I think it's frozen though. There's a planet with ammonia seas and ammonia rain. There's a lot of interesting things going on in our solar system. Yeah. And also studying the sun. People use adaptive optics to study the sun. We have a big telescope on Maui, a 4-meter telescope that's been looking at the sun. And there's also, as you know, some space probes looking at the sun. So the sun drives our climate change, right? So understanding what's going on with the sun would be a big help. I don't know that we can do anything about it, but it's important to understand.
Unfortunately, chat is not working, Miles. Is there some reason for that? I just got an email from someone.
I see a bunch of chat.
Yeah, I've got a pretty good list of questions still to go here.
Okay, good.
Well, Robert, we wanted to step away from the technical and science side a little bit for this next question. We'll certainly come back to that other stuff, but more on the public policy side. Question from Tom is, suppose some bombastic science critic berated you for spending tax money on astronomy when schools and food banks, et cetera, are chronically underfunded. How would you justify public science?
Yeah, to me, that's a really good question. One thing, I think astronomy, and especially Hubble, has inspired people to want to learn science. And, you know, I don't care if they go into astronomy. If they go into climate research, I think that would benefit the planet more. So, yeah, it's a balancing act. How do we spend our dollars? And I did a little research, and the NOAO budget, that's the National Optical Astronomical Organization. It's the government part of the National Science Foundation that funds optical astronomy. Their budget is $23 million. For radio astronomy, it's $86 million a year. NASA's budget is $23 billion a year, and $6.4 billion of that goes to science. So that's for those space telescopes mostly, and they're very expensive. And just like I said, so the NOAO budget is $23 million a year. And just for comparison, Tom Brady makes $23 million a year. So it's not a lot of money. Tom Brady is the Patriots. Was the Patriots.
Oh, hey. It's a sore subject around here. Now the Tampa Bay quarterback.
Well, I'm just saying, we spend a lot more money on football, and sure, that inspires people to go into football, but how many people can make it to professional football? I think, you know, if you're a poor student and you go to a state school, and I went to state school, you know, my dad didn't have a lot of money, and you can get a decent education and go into science in this country. And I think that's it's a lot, it's a lot more likely to happen than to make it to professional sports. So compared to professional sports, that's my answer. And that was a planted question, by the way, full disclosure.
So you're saying you have a better odds of being Robert Johnson than you do of being Tom Brady?
Yeah.
So Robert, one question I have for you is, we had talked about a video that you might want to show during.
Oh, yeah.
Are you able to do that?
Yeah, I can do that. Let me get it set up here. I had to pull it back up. Sorry, the power outage caused it to go away. Here we go. All right. So what I'm going to show you is just a video. Actually, I'm going to show you two of them. So I have to do the share screen trick. I'm sorry. I had this set up at the power outage. Took it away. Here it is. All right. There we go. All right. There we go. All right. So I hope you see that. So what you see here is what we call a binary star. This is one star orbiting another. Well, they orbit each a common space between them. And what you see here is the image through our 3.5 meter telescope that you see without adaptive optics. And what you'll see is, as I play the movie, that image dances around, and that's just scintillation. That's like and when you turn the adaptive optics on, that's what you see there. You see two points of light. And there's a tilt system that corrects the overall image motion. We turn that off there, we turned it back on. So that's one thing you can do. That just gives you an example. That's the headlight analogy. And I think I have some examples of a satellite. So here's a satellite. It's called CSAT. This was launched by NASA and the Jet Propulsion Lab in 1978. It was a satellite that was designed to study ocean heights using a synthetic aperture radar. And so this is without adaptive optics. You can't really see things. And I don't know, can you see my pointer here? I don't know.
Yes,
anyway,
I can see your pointer.
Try to describe it. It's dancing around, and then we turned on what's called the tracking. That's the image stabilization. And so it's not moving around, but it's still blurry. And there it is with the adaptive optics turned on. And you can see at the lower end, there's this, the synthetic or aperture radar panel. And at the top end, there's 2 solar panels. There's some antennas sticking out of it. And communications antenna is the bright thing in the middle. So that's just an example of what we can do with adaptive optics, what we can see on a satellite. So that's the 2 movies I had.
Robert, a related question from Gary. Can you talk about the hardware for the adaptive optics? Are you moving the primary mirror, the secondary or tertiary surface, and how many?
Yeah, so all astronomers do this, well, not all, most of them do it differently. We tend to, you have a main mirror to collect the light, and you have a secondary mirror to reflect that light to instruments on the back of the telescope. So for our system, we actually send the light through this complicated path, this elbow formation that goes down to a laboratory beneath the telescope. And so we have a deformable mirror there. It has thousands of actuators that can push and pull on the back of this sheet of glass. The glass is very thin, only 2 millimeters thick, less than 1/10 of an inch thick. And there's thousands of actuators. And we measure the turbulence about 1,000 to 5,000 times a second. And we have special sensors to do that. And the sensors are actually custom built for us in MIT Lincoln there in Lexington. And you know, without those sensors, this research would be impossible because we're trying to look at very dim things and make very fast measurements to correct for the turbulence. Military use for this technology is a little different than astronomers. So astronomers sit there and they look at the sky, and the stars move at what, 15 degrees per hour, right? Very slowly. We look at satellites. When we look at a geosynchronous satellite, it just sits there. It doesn't even move at the 15 degrees per second. But when we want to look at a low Earth orbiting satellite like Hubble, those things move across the sky in about 2 minutes. So our telescope has to follow that satellite. And so in effect, we're creating a very strong wind that blows across the aperture of our telescope. And that causes a lot of the turbulence to change very quickly. So where am I going with this? We have to update our deformable mirror thousands of times per second, maybe 5,000. But an astronomer, they only have to do it 500 or 1,000 times per second. And so different astronomers use different deformable mirrors. The Giant Magellan Telescope, they want to look in the infrared, so their deformable mirror is the secondary mirror. So they have the big primary, they have 7 of these big primaries, they have 7 deformable secondary mirrors, and then the light goes right into an infrared camera. And the reason you want very few mirrors is, number one, you lose a little bit of light every time it reflects off a mirror. But more importantly, if you want to look in the infrared, the mirrors at infrared wavelengths, the mirrors themselves are warm and they glow. So that causes a problem. So you want to minimize the number. The 30-meter telescope has overcome this by making all of their optics after the 3rd mirror, so that the 4th mirror is their deformable mirror. But everything after that 4th mirror, they cool it down. They put it in a large room that hangs on the side of the telescope, and they cool it down to, I think, -30 or something really cold. I don't know what it is. Something really cold. And so everybody approaches this problem slightly differently.
Robert, a related question to what you're talking about from Lee. How do they make such large telescope mirrors?
Oh, so the European extremely large telescope and the 30-meter telescope, those are made from a bunch of mirror segments, like 700 or 500 mirror segments. Each of those is about 1.4 meters in diameter. They're actually shaped like a hexagon, like a honeycomb. And so those are made just by normal techniques. Small mirrors like that are easy to make. The GMT is, the Giant Magellan Telescope, is a little bit different. They make those mirrors under the football stadium at University of Arizona. That's where I went to school. And what they do is they have a giant oven that's 8.4 meters in diameter. They fill that full of glass, they melt that glass, and they spin that oven about 8 times per minute. And when it spins, if you've ever taken your cereal in the morning and spun it, I don't know if you want to do that, but if you do that, it forms a shape, right? A bowl shape. And that shape is what we call a paraboloid. And that's the perfect mirror shape to make a telescope that, that is looking at one thing, not looking at the whole sky, but looking at one thing. And they melt the glass, it takes that shape, and then they turn the heat off and they anneal it. They let it to work out all the stresses and let the bubbles rise to the top over a long period of time, about a month. And then they start. And with that, if you spin the oven faster, you can make a very steep curvature. And by making this curvature very steep, you can make the telescope much smaller. And so that's how the biggest, what we call monolithic mirrors, single piece mirrors in the world are made under the football stadium at University of Arizona.
That's amazing.
Yeah.
Well, you can tell I'm getting hungry here because I'm wondering, are there any applications for the pizza making industry of a large oven that can spin like that? It's to a parabolic pizza. Other questions here right now. Sorry, we've got a ton of questions here in the chat and we're trying to get to them all.
Okay.
From James is, what is the role of computational power in the success of this technology? Is that an area where further progress might be made, or is there any sort of other obstacle?
Yeah, so computational power is not a problem right now. A lot of astronomers use graphics processing units to do the computations. We use purpose-built computers called field programmable gate arrays. But anyway, it's not really a problem. One thing we are, as an active area of research for us, is we'd like to use artificial intelligence and neural nets to optimize how we control the deformable mirror. This is the electronics that connect the wavefront measurement to the deformable mirror. And so as the conditions change, right now a human optimizes the system, but we've recently trained a neural net to do that optimization for us. And it actually does better than the human. And for us, because, you know, as the satellite's screaming across the sky in 2 minutes, they're constantly trying to keep up with the changing turbulence. But the neural net does a really good job of that. Yeah, another application is, I don't know if any of you are birders, but if you know about pattern recognition, that's a big area of research. You know, law enforcement uses it to keep track of us, you know, especially people in China. The government uses it to keep track of people. But, and then there's this app called eBird where you can use it to, well, Merlin actually is from Cornell. You can take a picture of a bird and show a picture of a bird to this large data app, and it can tell you what bird it is based on where you are, time of year, in the photo. We would like to do that with satellites. Can machine learning look at pictures of satellites and say, oh, this is something that we've never seen before. Hey, human, take a look at it. So that's another area of research.
I was just with a group of ecologists last weekend who were using an app like that to identify some plants they'd found out in the field, and we're so excited about it.
Yep.
A bigger picture question from Marin about the Big Bang. What have we learned about the origin of the universe, and have there been any modifications to that theory? And what is your view as informed by astronomy?
Oh, so I'm the person that makes the equipment for the astronomers. I don't actually know that much about astronomy, but so you probably know more about this than I do. I know one thing that we have been learning recently is about how the formation of galaxies occur from adaptive optics. So you can look at what's called Doppler shift. That's what I was talking about before. You know, if you've all heard a siren from an ambulance as it comes towards you and goes past you. It's higher in pitch when it's coming towards you and lower in pitch when it goes past you. The same thing happens to light from a star. And we can look at, you know, the stars have a bunch of different elements, and all those elements can absorb light. So we can look at and they absorb light at very specific frequencies. So we look at this pattern of frequencies, and we can see, is that shifted towards the blue, which means higher frequency. Is it coming towards us? Or is it shifted towards the red? Is it going away from us? And so with adaptive optics and some of the newer instruments coming online, you can take that light from, from different parts of a galaxy, and you can tell how the stars are moving and how fast they're moving relative to each other. And this is one of the clues that we've learned recently that pointed towards dark energy and dark matter. I don't know if you guys heard that podcast about, I forget what it's called, Shortwave on NPR. They had Space Week last week, and they were talking about dark matter and dark energy. And Einstein had a fudge factor in one of his equations that talked about the general relativity. And that fudge factor, he said, was his biggest mistake that he ever made. And he died thinking that he had made a mistake, but it turned out he was correct. There's a fudge factor, and we call it dark energy and dark matter now. And it really, we're really learning something about it.
I recently saw something about how they discovered a medium-sized black hole recently that they had discovered smaller black holes and supermassive black holes, and had found a medium-sized black hole. And, had been saying basically, like, here we are in 2020, 100 years after Einstein's work. What else might we discover that we didn't know about the universe 100 years from now?
Yeah, the theory before that discovery was that these medium-sized black holes couldn't exist. And there's some complicated reason, but we found one. So.
Kind of a side note question here for you. Is there any medical application of adaptive optics?
Yeah, people use adaptive optics to image the retina of living beings, humans. So as you know, there's liquid in your eye. We call it the vitreous and aqueous humor, and that liquid is turbulent. And so it doesn't really affect your vision that much. You might see it floaty now and again. But if someone's looking into your eye, it makes the retina itself very blurry. So they're using adaptive optics now to image the retina of living beings and, be able to diagnose different things about the retina and learn how it works so we can prevent and maybe detect early signs of blindness, like macular degeneration, things like that.
That's amazing. A question from Nathan. Was there a moment, or when did you know that this is what you wanted to do with your career? And what advice might you give students interested in optics or astronomy as fields?
Oh yeah, so basically for me, I went to graduate school for my master's in Ohio. Air Force has a graduate school there, and I didn't know what I wanted to do. And so I was just in the physics department, me and there's 12 other students, and we kind of picked things that sounded interesting. And I picked an area which was measuring turbulence. And so I got my first job here in Albuquerque, and I just fell in love with it. And that was in 1993. So my advice to anybody interested in science or math is just, study math. That's important, because even in science, math is, there goes my light again. Wow. Maybe someone could tell me why this thing keeps going out. Math is the power. I don't know. Math is really important. It's the language of science, so study math. I know it's kind of boring, but it's important. It's really important. And then just find something that excites you. And because passion is really important, right? If you work on something you're passionate about, that you can learn about, then that's something that I think could help move you along. And there's a lot of different areas to work on. If you want to help humanity, study climate. If you want to get into science, study ways we can feed people and give people water in this changing climate, and how do we survive this mess we put ourselves into.
A couple more specific questions here before we start to wind down. Wayne asks, what happened to the French group that you beat when your work was declassified, and are they part of the European telescope in Chile?
Yeah, they're part of the Europeans. We work with them all the time, and we meet with them all the time. We've really, the world kind of came together. There's competition all the time. There's even competition here in the US between the Arizona group and the California group, the GMT group and the TMT group. But we're all pretty friendly and we freely share information. Yeah, so we work with them. Yeah.
This is about the time that I would say, if you need to take a drink of water, you're welcome to. You're willing to keep, right? My giant Moby Dick beer here. So are you willing to keep answering a few more questions here?
Yeah, no problem.
Great. So Marin also asks, which of the 3 big new telescope sites would you want to visit first and why?
Oh, well, I'd like to visit TMT on Mauna Kea, but then that's just because that's where it belongs, even though some people don't want it there. I find it ironic that the Polynesians that made it to Hawaii and colonized all the way from Indonesia out to the middle of the Pacific in boats made essentially from grass, they navigated by the stars, right? They were astronomers, practical astronomers. That's how they got there. And so now I find it surprising that they're digging up cultural reasons to deny this telescope. Yeah, and there's already lots of telescopes up there. We offered to remove 3 telescopes to put this one there. Anyway, yeah, it would be TMT on Mauna Kea.
A comment from Alexandria, one of our New Bedford Science Cafe committee members. The physics department at Bridgewater State University is offering the first optical engineering bachelor's degree in Massachusetts. So that's some great local news.
Yeah.
A question from Gary. Since Starfire is part of the Air Force Directed Energy Directorate, can the adaptive optics enhance the focus of something like a megawatt laser on a satellite going outbound from Starfire or AEOS?
Yeah, it's funny. We're the Directed Energy Directorate, and we have a director, and he's the director of the Directed Energy Directorate. Anyway, yeah, so that's possible, but that's a line of research that we stopped a long time ago. We rely on space more than any other country. That's starting to change a little bit, but we don't want to create a space weapon or anything like that that could be used as a weapon. To start because we have a lot more to lose from that sort of technology. So that's something we abandoned back during the, if you remember Star Wars during the Reagan, we abandoned it back then.
Well, I think questions from the audience, if anybody has any more questions, please do submit them in the chat. But Robert, any last thoughts?
Again, I'd just like to thank you for Anne for inviting me and Miles for reading the questions and fielding the questions, and also to the Whaling Museum for hosting this. So thank you very much.
Summer student opportunity.
Oh, also we have an active summer intern program called AFRL Scholars. So you can just Google that, AFRL Scholars. You can, well, if it wasn't for COVID, you could even work at our Maui telescopes, and it's all expense paid, and it's a paid internship. And so I'll be advertising some topics for that in the spring, and it's for graduate students and undergraduates. Also, the National Science Foundation offers several educational programs for graduate students to work with the military. They get a scholarship, but they don't have to come work for the military. It's just to get them familiar with the military research.
I just wanted to thank you so much and remind everybody that there is going to be a recording of this that will be available in about a week. You can find it on the museum's YouTube channel or New Bedford Science Cafe's website. Robert, I have one last question. I understand you're going on a sailing trip to Antarctica in 2021. Is that trip still on?
We were just talking about that the other night. It's on a small steel sailboat, 56 feet, I think 8 people on the boat, and 6 of us are coming from the US, and we don't know where the other 2 are coming from, maybe 1. So we don't know. I mean, unless we have a vaccine, I don't see that happening. I don't see us being able to go on that trip.
That's too bad.
One way we could do it is travel to Argentina and then everyone quarantine there and have a negative test and get on the boat, but I don't see that happening. Maybe we could. But.
Well, we have a beer mug waiting for you when you get to New Bedford. And and we'll take you out for a few beers too. So thank you so much for being with us. And you didn't fade out on us after all.
Yeah, I'm happy the power stayed on. It went off, what, 3 times? 2-3 times? Yeah. So, yeah, I think the wind died down a little bit. So.
Miles, you did a great job. Where are you? Are you?
Thank you.
Yeah. So our next event is Tuesday, October 6th, and it's Jamie Jacquart. He's talking about carbon neutrality. He's Assistant Director of Campus Sustainability at UMass. Hope to have everyone back. I guess we're signing off. Thanks again, Robert.
All right, thank you. Thanks again for allowing me to speak. I appreciate it.
Thanks, everybody.